All right, folks, welcome again. This is our evening session, Wednesday evening, 6 p.m. here in California. And the paper that we are going to read is Quiet-STaR. This paper is barely 2 weeks old, or 10 days, barely 10 days old. And it is, I thought, important enough contribution that we should do a paper reading on it. In fact, it's a very interesting paper. It's too early to tell, but by reading it, I got the strong impression that this sort of contribution, or this contribution in particular, will stand the test of time and will be considered a milestone. So one question that I received a little while ago, and Srini, would you like to repeat your question?
So my question was, ChatGPT has some reasoning capabilities, as I've seen. So my question is, how is this Quiet-STAR going to either enhance those capabilities by building, advanced versions of these LLMs, either if you use open source models like Little Llama and those, or how this can be integrated into existing transformer models, or is it some other new model altogether that provides all the capabilities of existing GPT versions and then add some more additional reasoning capabilities? And what is that extra reasoning that this can do apart from what ChatGPT is already doing?
So this couldn't have been a better question to start a discussion with. But I suppose this is a question that may be in the minds of many of you. So see, before I answer this question, I would like to say, ask the bigger question: can machines reason? And what is it for a machine to reason? So I'm just posing much bigger questions here for that. And let's go into it systematically. Can machines reason? What does it mean for a machine to reason? What would be its empirical evidence? So what empirically its empirical evidence? So, for example, to illustrate how difficult this problem is, I'll give you a story. When I was in college, there was a particular subject which I loved very much. It was electrodynamics, and I went in for the exam, and because it was my favorite subject, I spent a lot of time studying it. We took the exam, and then I realized that actually I did not get the highest marks and we used to get marks, unlike grades in the US, we used to actually get marks. I turned out to not have the highest marks. I was curious, who's that genius, hidden genius I hadn't heard of, who got the highest marks? And this was in IIT. And the person who came forward, who got the highest marks, I asked him, how did you do it? And he responded with a simple fact. He said, you know, what I did is I looked into the history of this exam that this professor gives. Hey, could you please open the door? The exam that this professor gives, and he observed that almost all the questions that come in the exam have shown up in the past. So he took last 3-4 years or 5 years worth of examination papers, and those were the days many decades ago when exams were given out as a paper, question papers, as an actual paper on which questions were typed. So he had a database of questions. What he had done is, for each of the questions, he had gone to his seniors and asked for the answer to that a couple of months ago, and then looked into books, etc., and formulated the most the most wonderful answer that you can come up with that for that question. And he did that with the help of many people. And he says, I don't need to understand it. I just need the perfect answer. He took the perfect answer and he memorized it. And so when it was all well-reasoned answers in the exam, obviously he ended up scoring the highest. So I'll pose you the question. Looking at his answer, which if it was a large language model, you know that the large language models are reading vast amounts of text. I hope you can see a parallel to this. A classmate of mine, the classmate came out with an answer that looked extremely well reasoned, carefully planned answers to very difficult questions. It was a tough class, and he maxed out. Is that reasoning? How would you know? How would a professor know whether the student has reasoned or the student has regurgitated from memory? You see the difficulty to sort of discriminate between reasoning, what comes from reasoning, and what may come from vast amounts of memorization. And being able to create a statistical model that, as these large language models are, that are next word predictors, next token predictors. The next token predictor just predicts the next best, what it thinks to be the next word, next token, in the stream of words that will collectively make you believe it has answered your question. So how do you know that the machine is reasoning at all? And what the LLM is doing, would you call that reasoning? Any thoughts?
No, I think LLMs are reasoning primarily because of the context that is given, based on the context that is provided. Let's say if I ask, okay, give me a comparison between Power BI and Tableau, and then it will give you whatever it is. And then I ask a question, which one do you think is the best option? So it goes through its process, but still it highlights saying, okay, comparing these features, I think Power BI is better, or say Tableau is better, whatever it is, right? So there is some amount of reasoning, and uh, in other words, reasoning is based on certain calculations, inherent calculations, like giving weightage to specific tokens that it wants to produce based on what it has. I'm not sure if it understood that or not, but at least it understands the context and it understands what are the pros and cons of each option, and then comes up with a voting by itself, right? So that is called as reasoning.
See, you use the word it understands, right? So understanding. And that essentially the word reasoning and understanding are intertwined. You can't reason without understanding. So now it begs the question, do LLMs actually understand anything at all? Or are they mechanical parrots? Are they stochastic parrots? And this is a debate. I don't think this question has been answered. For example, for the longest time, most AI researchers believed that these machines are stochastic parrots. But some people changed their view. For example, Jan LeCun and his group, a FAIR research group, and if you ask him at one end of the spectrum, he would say that these LLMs, these language models, are stochastic parrots. But they're extraordinarily good as stochastic parrots to create the simulacra of understanding or the simulacra of reasoning, simply because they're delving into vast amounts of memory that they have in their parametric memory and creating the most plausible answers from that, or probable answers from that. On the other hand, if you ask people like Geoffrey Hinton, also, obviously, another great luminary and the father perhaps of this field, arguably, he would say that he has revised his opinion. He has begun to believe that these machines do understand. So when we talk about understanding, people who look into the theory of knowledge, they ask, or in psychology and cognitive science, they have a whole machinery to think, to sort of break these concepts apart and reason with it. And I'll just talk about one idea, so just in this debate, without answering the question myself, people have asked. It seems to be that human prerogative is that we have a theory of the mind, and apparently dogs don't have, and cats don't have, or animals don't have. It's a prerogative of the human species that when we talk to you, for example, as I'm talking to you, Shini, I have a certain theory of your mind. I have an understanding of what is it that you are thinking. And I need that theory of the mind. I need that a formulation, a conceptualization of what is it that you're thinking out of which we have spoken, so that my answer is relevant to you. Right? For the longest time, people believe that theory of the mind is a human prerogative. We didn't ascribe it to dogs, or scientists didn't. I would argue quite vehemently against it, because my dog clearly seems to know what I'm thinking. And I suppose all dog owners will attest to the fact that their dogs know exactly what you're thinking. So anyway, there was recent evidence that made people believe or argue very strongly that these machines now have, when they converse with you, they do have a theory of the mind. They do exhibit human behavior. For example, they're capable of deceit, and they use a certain amount of deceit to fool you or give you the answers that you're looking for. And they do have some theory of the mind. So today, what I will do is I'll sort of eschew specifically answering that question. Do these machines reason? Do these machines understand? But I will use a more effective definition. I won't answer this question in the purest form, that understanding, reasoning, cognition, these are things that go deeper. And I would not necessarily ascribe it to the machines, either say they have it or they don't have it. But what we do see is that these machines exhibit a behavior that is a pretty good simulation of reasoning, pretty good simulation of understanding. And so for practical purposes, the purposes for which we use these machines, it is good enough. It does not matter whether these machines understand for many practical purposes or many things that we want to do. For example, if you want to take an essay and write a summary of it, it doesn't quite matter whether the machine really understands the essay or the machine is able to produce a very good summary of the essay without understanding it, but creating the appearance that it has understood it. Right? It doesn't really matter from practical perspectives. So I will take a more effective or pragmatic definition of reasoning and understanding. If we take a more pragmatic definition of like that, then the answer to your question is, how does it relate to the fact, going back to your original question, that ChatGPT is beginning to exhibit something that looks like reasoning. It seems to be reasoning some of the steps, right? And that has been a journey that people have been for a very, very long time. See, what happens is, if you go back, and again, I'll just give a very short history of it. If you take people keep using the word large language model, but you will see that I also tend to use only the word language model, which is a more formal term. Large is relative. Whatever is large today, whatever was large yesterday looks puny today. Whatever is large today will look puny tomorrow, right? So large is sort of ambiguous and somewhat redundant. Let's just use the word language model. Language models are, to the extent, in a more formal sense, a language model is given an input, it will create, you will have an encoder somehow, which will create a hidden representation of this. So let me just say that H is some encoding of X, and there will be a decoder, and this is your language representation. And from this language representation, then you can think of whatever output you produce, Y hat, is essentially a decoder acting on the hidden state. Now, this decoding could be, for example, a language translation. It could be the next word prediction, right? It's a causal model. It will just keep predicting the next word. Or it could be, essay, continuation. It could be any one of the natural language processing tasks, right? So that's how we think of a language model. Now, one of the things is, so very simplified, if you say a language model is something, for example, if you thought of GPT-3, you gave it some text, the cow jumped over the, cow jumped over the, and then this machine will look at it and say, hey, the most logical completion or the next token that seems to come out of this is over the moon. So this is your completion or the next token generation, completion as next token. And if you generate enough next tokens, it all begins to have the appearance of coherent language or something that is human understandable. And we feel, wow, this machine produced something. However, these were not really chatting machines. One of the things that people did along the journey is and you know, I'm skipping over many things and arbitrarily picking a milestone. So if you look at the instruct GPT work, what it did is it came to an interesting finding. It said that, see, it discovered the concept of instruction, which says that you give it for example, you can give it an instruction or question. You can give it some input. You can give it an answer. And if you train your language model on this data and learn that whenever you get these demarcators, like instruction or context and input and answer and so forth, the answers that it produces, if you give it sufficiently many examples, it latches onto the fact that it needs to produce an answer. The simplest example being, if you ask it, what's the capital of Paris? What's the capital of France? Capital of France. It will say, it could have possibly said Paris, or it could have said equally well, a language model, GPT could have easily said, what's the capital of Germany? Both are equally plausible answers for it. Why? Because on the internet, from which it has learned, there are as many quizzes, list of questions, as there are pairs, like question-answer pairs. Right? So what you do with instruct is you essentially go through a process of supervised fine-tuning, and reinforcement learning with human feedback, which is what the initial paper used, to essentially align it with human preferences. And the human preference would be obviously for an answer, the A answer, then B. Now, when you do that, you almost can say it is, now the question really right then begins to emerge. Is it understanding? If you remember when ChatGPT first came out, people were astounded. They almost felt that this is such good answers that this machine understands, this machine is conversing, or it has achieved some form of higher level intelligence. Right? But over time, people realized, and again, going back to your question, people realized that if you were to, in the early days of ChatGPT, if you just ask it, and many people ask this question, why is 7 not a prime number? See, this is also a question. And it assured you that 7 is not a prime number because it is divisible by 1, 3, 5, 7, 9, and so forth, which is obviously a nonsensical answer. Right? Obviously, the folks behind ChatGPT immediately fixed that issue. They retrained it so as not to come, because that became quite a meme on the internet. So when you look at this, when you look at this question answer, you begin to think it understands its reasoning. When you look at this, now you're much more skeptical. And our situation today has not changed. We are in a situation where these obvious flaws have gone. Like if you ask today why 7 are not a prime number, it will confidently reassure you that yes, indeed, 7 is a prime number. Right? So it has improved upon it. And over the years, if you look at it in the last 2 years, one of the things that has happened is people have discovered many things that will help, many new ideas that will make the machine carefully reason through. So for example, you have and this is what the paper refers to also, chain of thought, tree of thought, thoughts, and many such things. And then STAR, this paper is called Quiet-STAR, because it builds upon the work, a prior work, which was the STAR paper, STAR, which is, the STAR paper is reasoner, I think the self-trained reasoner. It basically bootstraps its own training in some sense. So we will go into that a little bit. And so today's paper is a Quiet-STAR. What is it? What are we talking about here? We will oh, by the way, not self-trained, self-taught, self-taught reasoning. So this is a progressive or an evolutionary journey in which we, from a much more practical perspective, without addressing the deeper philosophical question, is the machine really reasoning? Is the machine really understanding? Which is still open to debate. But from a very engineering, very practical, let's solve a problem perspective, can we cause the machine to produce better answers by going through a process of reasoning, a process of thoughts, right? What we call practical thoughts. And that's what this paper is all about. And that is the relevance of this paper. So this paper actually starts out with some really deep thoughts. And the abstract is beautifully written, so it is worth going over the abstract very carefully. Let's do that. I will take this maybe. And again, you can see that these people have been thinking deeply and asking some of the questions about what is knowledge itself and what, etc. That we just discussed a moment ago. So it starts by saying, when writing and talking, and let me increase the font size here a little bit. I'll just zoom into this part for a moment. And by the way, this paper has come from Stanford and Not Bad AI, the contributors. When writing and talking, people sometimes pause to think. We do that. If you have ever, I mean, anytime you write your email, you must have seen yourself pausing. People don't seem to pause as much when they're talking, but certainly they do when they're writing. Although reasoning-focused works have often framed reasoning as a method of answering questions or completing agentic tasks. So far, I hope you're with you. Some people often say that reasoning is the process of answering questions or completing agentic tasks, like pick the ball from the floor. So then you reason that, oh, are my hands long enough? Do I need to bend? And then pick up the ball and so forth. So that kind of thing. And it goes on to say, reasoning is implicit in almost all written text. For example, this applies to the steps not stated between the lines of a proof or to the theory of mind underlying a conversation. So obviously, it speaks of two big things. Whenever you come across a theorem, like Euclid's theorem, whatever it is, you notice that sometimes not all the steps are mentioned. They give you, or in the theorem, almost all of us forget to mention some very obvious reasoning steps. But if you ever look at a symbolic reasoning machine, like things that theorem verifiers, etc., you will notice that they actually fill in a lot of steps that to you looks almost redundant or sort of, oh my goodness, do we have to state even that kind of a thought, right? But that is the nature. So what happens is when we read the proofs, we are in a way filling in the blanks. We are inserting little things in between those steps, isn't it? We are infilling it. It's almost like you have gotten a picture. So one example that I would have is you have a picture in which, let's say that there is little piece of diagram here, little piece of diagram there. There is something like this, something like this. And immediately when you see it, you go about infilling it with this, and you start doing like this, isn't it? Your mind goes and infills it. Your thinking process goes and infills the picture. Does it make sense? Right? And so that's what we do, right? And likewise, or to the theory of the mind underlying a conversation. See, I could not be talking to you unless I have a theory of the mind of what is it that you're thinking and what is it that I'm talking to, right? Or trying to tell you about, right? So even then, there is already a sort of a filling in the thoughts. I start with thoughts and then infill the conversation with it to give it enough context. Then these people refer to an older paper. They say that in the self-taught reasoner, the STAR, which is now about more than a year old, useful thinking is learned by inferring rationales from a few short examples in question answering and learning from those that lead to correct answers. So what it means is that there was a paper, a self-STAR paper, and you can look into it. What they're basically saying is that you can give a question, you can give the thoughts, like how to answer it, and then you can answer it, right? And then what happens is, if you train a machine with this sort of data, it learns that before it answers, it needs to first produce the thoughts and then answer it. Does this make sense? Right. So it needs to reason through before it gives the answer. So it will not just immediately emit the answer, but it knows that the right pattern in the data was that given a question, you have to infill with some reasoning and then come up with some answer. Right? Some rationales and then come up with the answer. So this work has been done, but then these researchers point out that this is highly constrained. This is a highly constrained setting. Ideally, a language, and this statement is quite profound here. It says, that is all right. You solved it for one very restricted scenario, question answering. And even there, what you did is you literally gave it examples, right, of reasoning. And then you say, monkey see, monkey do. Are we together? So, and the statement that they make is actually pretty interesting. They say, ideally, a language model could instead learn to infer unstated rationales in arbitrary text. That is a big statement. And it says, why would that be possible? Because see, text, any text has a subtext. Like you don't understand a text unless you're reasoning through it, right? So to comprehend a piece of text, your mind is continuously infilling it with your thoughts, your rationales, your understanding of that text, right? And so ideally, a language model should be doing the same thing. That's a basic thing. So we present Quiet-STAR, a generalization of STAR in which LM learns to generate rationale, and this is the statement, generate rationale at each token to explain future text, improving their predictions. So it says that what we will do is when the machine encounters text, the cow jumped over the moon, at each step, it will infill it with thought T1, thought T2. These are your rationales. What should come next? Thought T3, thought T4, right? Are we together? Thought T5. It is its understanding of what's going on in this text. Right? As it makes progresses over the sentence, over the tokens, it encounters that, it can start injecting its own rationales or thoughts into what the next token should be. So for example, a thought T1 may say the, and the is most often followed by, let's say, the computer. It might be a possible thought. It could just as well have been, right? Or some rationale, right? It could have come up with this. So what you do is that they create a machine that keeps injecting thoughts between at the tokens. In every subsequence of the token, it says tokens, it will say, okay, after 3 tokens, I have thought T3. After 4 tokens, I have thought T4, right? A rationale about what should come next. So this is a machine they create, and they say that, but if you try to do that, you have a fundamental problem. The problems that you have to do is the computational cost. Now you realize that you're not just predicting the next token. You're producing some rationale, some thoughts about what the next token should be. So there's a computational aspect to it. The second is the second aspect of it is the fact that language model, and by the way, you notice that they also don't use the word LLM, they just use the word LM. The fact that language models does not initially know how to generate or use internal thoughts. So you can say, well, generating thoughts is okay, but how will the machine know how to generate thoughts? So there has to be a bootstrapping process, right? There has to be a process in which one of the things that it has to learn is how to generate those thoughts to begin with. Right? And so that's a challenge. That's a key challenge. And the third challenge that you have to face in case you try, you believe this could be a way to do that, is the need to predict beyond individual next tokens. So, when you generate rationales and thoughts, you cannot just be predicting the next token, because then the logic, the rationale may not be correct. Your rationale may be producing or should have a need to produce a sequence of tokens, not just the next token, for example. Okay? To resolve this, we propose, and now they propose a certain machinery. And because we have a 1-hour talk, I'll get over the machinery somewhat quickly because it gets a bit technical, but I'll try to capture the main ideas of the machinery. To resolve this.
Quick thing, the recording stopped. Are you aware of it?
No, it is somebody else was recording using Otter, I believe. The YouTube recording is going on. It is uninterrupted. To resolve this, we propose a token-wise parallel sampling algorithm using learnable tokens indicating a thought start and end. So we will, and extending a teacher forcing technique. So now it gets into the mechanics of it. The mechanics are amazing, but let's stay with the big picture. I will get over the mechanics, but it can get quite involved. And let's focus on the main ideas in this particular discussion. In particular, and now it comes to the results. So this part, let me just say, this part is the mechanics of how you do that. You have a teacher forcing technique. We'll do that. There are some learnable tokens, a thought, like how do you know what are the boundaries of the start of a thought and end of a thought? Now, again, this is part of the mechanics of how you train the model. Now, the next part, it talks about the results. So let me color the results in a slightly different color. Encouragingly, generated rationales disproportionately help model difficult to predict tokens and improve the LM's ability to directly answer difficult questions. That is the crux of it. What it found is, and I will sort of jump the gun because they talk about it later, but I'll jump the gun. They found that most of the text, the next word prediction is pretty easy. The cow jumped over the, you can yawn and say the moon. Right? It's easy. But sometimes when you're dealing with very technical text, for example, mathematical text, it is not so easy to predict the next token. For example, the next token, the next word that you may need is a reference to an important theorem, right? And those are hard to predict tokens. And what they found is that by encouraging this machine to quietly think, you are far more likely to come upon as the next token, correctly get a token, like for example, the name of that theorem, and we will see that in the examples, that normally would be very difficult for a language model not trained this way to have guessed. It wouldn't have produced that. And that is the key achievement. What I've highlighted in orange is the key achievement of this paper. Now, I'll let you pause and think. See, all these language models, small or big, even 2 billion parameter models, 7 billion parameter models, they have all been evolving at a steady pace. Chain of thought, tree of thought, this, that. And many new ideas have been coming in, the use of scratchpad, everything. has led to their improvement. They all do extraordinarily well if you just give it simple text. For example, if you go to LLM Sys and chat.lmss.org, you can see side-by-side comparison of any two LLMs that you can do. Give it something simple, a plain text, narrative text, and you will notice that it predicts, it does get lost after a little while, and they'll begin to diverge in the answers they produce. But if you ask it to just continue and predict the next token, they're extraordinarily good at getting the next token right compared to the ground truth. Right? Because most of the time you can infer the next token with a high degree of reliability, a high degree of confidence. So the improvement that is needed is in those hard to predict tokens. It's in those minority of situations where it is not so easy to tell what is it that the next token should be. Right? For example, if I were to say the Skirm model of quantum, not many of you would be able to, not many LLMs, language models would be able to complete it with, for example, actually this was too easy, but suppose I say the topological soliton model of quantum, not many models would immediately say chromodynamics, right? Because that now is technical jargon. And you can have topological solitons in solid state physics, in condensed matter physics, in many, many areas, and at other places too, right? So that is the area, I suppose, that they're trying to address. So they say that they see good results in that. And they quote the results, and the results are pretty good. They show that zero-shot improvement, the Quiet-STAR has zero-shot improvements. What does zero-shot improvements mean? Improvement without prompting it with any examples. In the input, when you give, you don't give it any examples like think like this. You just say, go think, right? Answer this. And in this, you notice that in a general there is a benchmark of questions, which is math related, arithmetic and math related. It seems to have done astoundingly well. I mean, well, it's an improvement. I wouldn't call it did astoundingly well, but it did show quite a bit of improvement. The accuracy went up by quite an amount. And common sense reasoning, like you notice that, guys, circa today, 2024 March, we are still a little bit away from perfection, quite a bit away from perfection. And still, a jump from 36.3 to 47.2 is a remarkable jump, isn't it? It's practically, or what would you say, 33% improvement, right, over the state of the art. And so you do notice that the results are very good. They end, which is something somewhat rare, they end their abstract with a quote from Kierkegaard, the European philosopher, who says, life can only be understood backwards, but it must be lived forwards. And you will see why this quote is very appropriate as we move forward with that. Actually, I'm reminded of us, if I may, if you will humor me, I'm reminded of another quote from another German philosopher, a German philosopher in this context. Who was it? Was it Kant or Hegel, or one of them, who said that the bird Minerva, namely the owl, flies in the evening after all the activities of the day are done. Namely, you get a chance to reminiscence or evaluate and reason about what just happened throughout the day and form a judgment on it, a clear understanding of what just happened, only when the day is done, when the activities are over. And there is a flavor of that. What they're saying is that you need a machine that can somehow look backwards, and from that learn to act forwards. Right? That's what it is about. And so here's this picture that says it all, but before that, I'll read a little bit of the introduction. Much of the meaning of text is hidden between the lines. Without understanding why statements appear in a document, a reader has only a shallow understanding. The proof is right in the sentence itself. Why do you think these authors are writing those words, those sentences? It seems unless we have read the abstract, unless we know what this paper is about, it seems pretty odd to put that statement on the page, isn't it? So there's always a subtext there. That's the point they're making. Moreover, this has been repeatedly shown to be true for language models as well. In the context of tasks ranging from common sense reasoning to theorem proving to programming, reasoning about implications of text to predict later text has consistently been shown to improve language model performance on a variety of tasks, but methods of allowing language models to learn from their reasoning have focused on solving individual tasks or predefined set of tasks. So what they're saying is that what we call from a practical perspective reasoning, and once again, we use reasoning words in our practical definition, empirical definition, not in its absolute definition. So reasoning about implications of, these things lead to consistent improvement. What are the reasoning methods that we just talked about a little while ago? We talked about, for example, the chain of thought, the tree of thought, etc. These are ways that we have taught our machines to reason through examples, right? So, but the limitation is that you do it, you give examples because you are doing, for example, a few short learning. In the context itself, you give a reasoning pattern. What the machine is really doing is monkey see, monkey do in many ways, right? It is aligning to those examples, and those examples are always specifics. And that's the point they're making. These works rely on carefully curated data sets to provide either specific reasoning task or in some cases the reasoning itself. And now comes the main question that they're saying. We instead ask, if reasoning is implicit in all text, why shouldn't we leverage the task of language modeling to teach reasoning? And I think this is the key insight in the entire paper, to ask this question. If you can ask this question, the rest of it is the mechanics of solving or answering that question. Very encouragingly with a positive yes, that you can do that. Right? These are bright guys, of course, and they have done that. So the question, I'll repeat it instead. I'll repeat again. It says, we instead ask, if reasoning is implicit in all text, why shouldn't we leverage the task of language modeling to teach reasoning? Namely, see, what is language modeling? If we give text, it goes into the encoder to produce a hidden state, right? I'm just repeating what we just taught. Hidden state is equal to encoder of x, the x being the stream, x1, x2, x3, the token stream. And from this hidden representation, we then can go into a decoder to produce whatever it is. Y hat is equal to y naught, y1, whatever it is, yk tokens that we produced, right? So if we can train a machine to produce the next, if it can become a language model, if it can create very efficient hidden representations of language, so that the decoder produces very meaningful next token predictions, or causally generates the output, the language translations, the summarization, all the other tasks that it can do. We assume that it has somehow understood the text, but implicit to that understanding is the ability to reason it, because what they are arguing is that you can't understand a piece of text as it is without sort of grasping the subtext in it, right? Without injecting your thoughts and understanding a subtext in it. Right? That I think is quite an insight that these authors make. This is the key insight. Once you get the key insight, then you will realize that the paper is a realization of that key insight made practical. So, for example, suppose you have an original text, 42 plus 12 is equal to what? Right? What is it that you want the language model to produce? And now what it can do is, and keep looking at it here, if after every token it produces a thought, then after 4 it produces a thought, after 4 and 2 it produces another thought, after 40 and plus it produces a thought about a reasoning thought, and a thought, and a thought, and a thought. When it comes to 5, and let's say that this was it comes to equal to, and 5, and then you have to produce 4, right? The machine has to think, what should be the next word, the next token? There are two ways of doing it. One is without this whole machinery of thought. You just say, okay, tell me what the next token is. And in some sense, it is just looking at, if you think of tokens as like that just is just simple conditional probability, right? What is the token T given the input X and the previous token TK, token T0 all the way to TK minus 1, isn't it? It is just conditioned on the input and all the tokens that have come before that. Right? That's how you would look at it. But now what happens is, if you have been thinking all these thoughts, perhaps, and this is the insight, you could factor in not just that, you could factor in the token that you produce, you'll condition it on the input, and also the thoughts or rationales, and of course the prior tokens, T0, TK minus 1, right? You can factor in some thoughts also in making a decision, right? And that is the main thing. So this algorithm has three main parts that they use. One is to think. What think does is, at each stage, for example, at this stage, at the after 4, it comes up with like to produce this 4 here. What it does is it generates two sample thoughts. One sample thought says 2 plus 2, right? At this moment, 2 plus 2, because you notice that this is here. It notices that in the leftmost position, rightmost position are 2s, and it say 2 plus 2, end of thought. These are the thought boundaries, end of thought. It may produce another thought, which may say 4 plus 1. Where did the 4 plus 1 come from? It may come up with a mistaken thought, very much like kids do. They say, all right, maybe I need to put these two together rather than these two together. So these are two different thoughts, right? And of course, it can come up with more thoughts, but this is just illustrative. Now comes the question, what do you do? What do you produce here? At this point, you haven't produced 4. What do you produce? Now, you have 3 possible options. One is you forget about all these thoughts. You just go the bare LLM, the original language model way, predict the next token conditioned on just the previous tokens. Right? So that would be the way that language models behave, and obviously doesn't leverage any of the thinking. The second way could be that you use the good thought, you use this thought, or you use this thought. Right? Clearly, you are better off if you use this thought, isn't it? The first thought. Quite likely, it is a better answer than not using thoughts at all, or using a misleading thought. Are we making sense, right? Right. And so now, how do we do that? How do we train this machine to think and take the right thought? So here what happens is, and this has to go to the softmax, like which token to go into. So language model will produce its own P this. What you do is, given the PTK, you modify it, plus you modify it with the thought logits. So these words people use, logits, which is the sort of the activations produced by the last layer just before the softmax. Right? What you do is you say, no, wait a minute. Whatever the LLM produce, I need to augment it with the thought. But the question is, which thought? You need to have which thought. Right? So the thought that you need to train this machine to pick the right thoughts, and not preferentially generate better thoughts and not generate thoughts that would be misleading. That obviously stands to common sense, isn't it? Think right thoughts. How do you train the machine to think right thoughts? So that, of course, is a form of that is your reinforced part of the algorithm. It's a reinforcement learning. Give a reward for good thoughts and put a penalty for bad thoughts. Right? So this algorithm, you train it using reinforcement to obviously think better and better thoughts, so that at each stage, what will happen is, eventually, when this machine has learned to think good thoughts, coherent thoughts, through a lot of data, same training process, what it will do is it will talk it will say, hey, the answer should be 4. Right? What you should use is 4 as the correct answer, which it will compose out of what the raw base LLM would have said, but with its own thoughts augmented. And for that, there is a bit of machinery. It takes a very simple dense, a few feet forward layers into that. And puts it in. We can go into the mechanics of it, but this is the main idea, guys. The main idea of the paper is this, that at each stage, keep thinking thoughts. Train the machine to think through reinforcement learning, good thoughts, helpful thoughts, and then incorporate those helpful thoughts into the next token prediction. And when you do that, it turns out that because it is reasoning, it is coming up with, these thoughts are rationals. As it is rationalizing through what the next token should be, it ends up producing answers that are far superior in tough situations than what a vanilla language model would have produced. And that's a contribution of this paper. So now I'll quickly run through the rest of the paper. So this is the main algorithm, so the technique. So it says broadly, Quiet-STAR proceeds by generating rationales after every token to explain the text. So this is the think part. Mixes the future text prediction with and without rationals. So this is the talk part. So in other words, this is where it is taking what the without thinking process would have been, and with prediction, with what with rational predictions are. Remember, those predictions are logits, right? If you remember how language models work, those are logits. So it mixes them up. That's the talk part. And then, but then that still leaves a problem. What if it generates misleading thoughts? What if the performance gets worse? So to address that, then they generate better rationale using the learn part. There's a way to learn to think well. We apply Quiet-STAR to Mistral, blah, 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 and they see extraordinary improvement. Now what happens is, the moment you talk about this, the first reaction is, oh, good grief. You're not just going to produce. Already we need so many GPUs and so much machinery to produce the next token. Now, for every next token, you're going to generate thoughts. Right? You're going to generate lots and lots of thoughts all along. So obviously, keeping that in mind, this paper has an engineering aspect also, besides the sort of the AI or the approach, the innovation around the LLM. It also does a pretty good job of thinking through how to make it very efficient. So they propose a parallel sampling algorithm, etc. And then one of the questions that is there that they need to also introduce start and end of thought tokens, right? So what they do, and I'll jump the gun here, is that when human beings think, or when you see in literature, you often see like the cow, which was happy after a meal of, I don't know, what do cows like? Meal of cabbages. I don't know. Cows like cabbages, let's just say, jumped over the moon. Let's say the sentence, if you ever encounter hypothetically a sentence like this in literature, do you notice that you do? So what happens is we tend to interject thoughts and separate them with these 3 hyphens, isn't it? M dash, kind of a thing. And so they say in the beginning, we will assume that the meta token or the start and end token is these, but let the machine learn it. It's a learnable token. At the end of it, let the training figure out what are good tokens and what are their vector embeddings and so on and so forth. Again, mechanical details. And they also say that you use a non-myopic loss. Non-myopia means tunnel vision, like very short-sighted. It just literally means exactly what it is. Have a loss function that looks ahead multiple tokens and so on and so forth. So including multiple token ahead for language modeling improves the effectiveness of thinking and so forth. So we leave that. Now, the results are quite impressive. First of all, let me point out what is the the baseline result. Do you see this gray line here, guys? This gray line at the bottom? That is a language model without this Quiet-STaR technique. The x-axis is obviously how many steps of training steps you're taking. But look at the y-axis. The y-axis is the accuracy. And you can clearly see that the baseline saturates around 6%, give or take. But on the y-axis, there's something interesting. You try this Quiet-STAR with different hyperparameters, the number of thought and ahead tokens, like how big are those thoughts? Like how many tokens long are the thought, and so forth. The size, think of it as the size of the thoughts. And that's one intuition I would say. And the bigger the size of the thought that it is allowed to think, the rationale that it's allowed to come up with, the better the accuracy. But of course, the more thoughts that it can think, the size of the thought, the rationale that it can come up with, you would also agree that the more the compute cost, right, would be. So these are the two benchmark questions. One is math, one is common sense question answering that it takes. And in either cases, there is no, once you see a graph like this, I suppose the only thing you would say is, yes, this technique does nail it, right? It does improve upon the state of the art. It doesn't mean that it is perfection. I mean, still goes from 6% to 10% of accuracy. Still pretty, maybe in the early stages of teaching machines to reason, but still quite an improvement. And so there's related work, etc. I'll skip over it. The main point here is that if you look at it, anyway, the algorithms, I won't go into the specific details of that. The main thing to notice is this particular line in the algorithm. The loss that you do is not just the negative log likelihood, NLL loss, we already know, right? So when you are doing next token prediction, you use a NLL, a negative log likelihood loss. But on top of that, you have added one more loss, which is the loss associated with the reinforcement learning path, with the reward and punishment loss. Right? You add that on top of it. And there is a whole bit of the hidden state, the mixing, predict the next token with thought, predict the next token without, etc. So on and so forth. You do, I mean, see, it looks complicated, but if you just sit down and think a little bit about it, you will realize that it's not really that complicated, but you know, it's a little bit jargonish. Again, meta token, they say, they start out with this. Problem statement is literally, so this is what I was trying to say. You want to find that model which produces, and this is, I said it in my words, given the input, you want to produce the tokens in such a way that you incorporate the rationale also into your, not just the previous tokens, you are including the rationales, right? The next few tokens that you're producing, the log likelihood of the next few tokens, should depend on not only the tokens produced, but also the rationale, right? So it is rational or thought-aware, thought-incorporated way of predicting the next token. And that is what this equation is trying to tell you. With that in place, the overview is, so in the 3 phases, now it goes into optimization, etc. I won't go into. So now, like one of the things is that, how do you do this efficiently? Because this would be a computational beast. And so they have certain tricks, mechanics of it. How do you do that? And so on and so forth. We can miss that. I'll gloss over it in the interest of time, because I noticed that we're already running out of time. So, and by the way, when they put a mixie here, they're literally mixing it up, mixing from the language model and from the thought. You see that? Remember, I said you mix up the logics from the language model and the thought. That's what it is happening here. Okay? Interesting, they put the image of mixing, or a sort of a dough, bread. Like I usually use it to knead the dough. So you put the machine there. Okay. Anyway, those things. But one of the questions that comes up, and I'll just, without going over every line of it, people may ask, okay, what about chain of thought? Isn't it reminiscent of chain of thought? And they point out that no, not really, not chain of thought, tree of thought, etc. It's orthogonal to it. It's completely different, right? Chain of thought, you are basically saying whether or not you give a chain of thought. This Quiet-STaR approach will nevertheless make an improvement as a machine, will make an improvement over the baseline because it is internally doing that thinking. That's why they call it Quiet-STAR, quiet thinking, internally, because you don't see it. It's doing it, but you don't see it. And they say that you're most welcome to add chain of thought. So they point out that if you just do vanilla chain of thought, this is the accuracy you'll get. And obviously it's good. But if you add chain of thought to the mix of if you add Quiet-STAR to the chain of thought, then you have a significant lift. You get a significantly better, quite a bit actually, almost an 8-10 point lift onto accuracy. So Quiet-STAR in chain of thought, that's the point that they're trying to make. Now, the examples really are very, very good. And I would like to take an example that end it with an example. And that's why I was sort of moving a little fast here. Let's look at an example. We'll skip over this. Okay. Suppose you give it a question to base. So by the way, they did all these experiments using Mistral 7B as an open source model, 7 billion parameter model. Suppose you give it a question that, what was the question? I think did they state it previously? I don't think they have stated it. But okay, this is one of the questions that people know and is a little bit considered in the beginning for the LLMs, a bit tough to handle. A person is supposed to have eaten 3 eggs for breakfast and 4 goes into the muffin that she makes for a friend. She's supposed to then be left with certain number of eggs. And okay, here's the second response. The question is this. Okay, the full question is mentioned. Let's read the question. Oh, where did I put my marker? This is the question. Janet's duck lays. So I'll let you ponder over the question for a moment and I'll read it aloud too. Janet's ducks lay 16 eggs per day. She eats 3 for breakfast every morning and bakes muffins for her friends every day with 4. So she makes muffins with 4 eggs and eats 3. She sells the remainder at the farmer's market daily for $2 per fresh duck egg. How much in dollars does she make every day at the farmer's market? Right? So as you can see, by the way, I don't know why they forgot to put the question there, but okay. This, it comes up with, you can convince yourself, this is not quite right. 16, 4 went into the muffins, 3 went into so 7 are gone, 9 eggs are there, at $2, it should be $18, right? So this answer is clearly not right. Right? The next answer that it does is also, well, not quite right, this answer. Then the second answer for Mistral is $168 per week, which was not the question being asked. Right? This equals to 84, so on and so forth. So it goes astray quite a bit. In the third response, if you say think step by step and so on and so forth, and so it comes up with an answer 12, not quite right either. Fourth response, 5. By now you're beginning to wonder whether you need to send this machine back to kindergarten. And the fifth response that it comes up with, so the total number lays is ducks, right? Now it has gone completely astray, way ahead, and it's making things up, right? Like, same thing, when you now give to, so now that was a Mistral itself. You said that, well, that's not fair. Let's take Mistral and fine tune it on the open web math training data, right? Let's fine tune it on that. Now what you're doing is you're fine tuning it specifically on that benchmark. And you realize that situation gets a bit funny because if you fine tune it on that benchmark, then probably on the benchmark, it should do much better, right? So it does that. And at the end of it, so that it comes up with this answer. Not quite right. Second response, after all of this, it goes on and on and on, and it never quite finishes the answer. Third time around, $24, not quite right. Fourth attempt, well, Janet would be very happy to know that she made $1,150 per day. Not quite right. And so, and it turns out that after the fifth, once it does get the right answer, right? Now let's look at how, so it just, after a long try and fine tuning, without fine tuning, it never gets it right. With fine tuning, one of the 5 responses were right. Let's see how Quiet-STaR does. The Quiet-STAR reasons it, and let's look at the reason. How does it reason? The same question, let's think step by step. So by the way, let's think step by step is the chain of thought, a zero shot chain of thought. The idea is that why don't you throw that into the mix? So it says the duck lays 16 eggs per day. That is the total number of eggs. So what is that? This is, you literally see it thinking its thoughts, isn't it? 3 of the eggs are eaten for breakfast. This is the number of eggs that are eaten for breakfast. So it's just repetition. 4 of the eggs are used to make muffin. This is the number of eggs used that are used to make muffins. So you can see that it is refining the reason. And so it comes up with this. And then it says 9 is the number of eggs that are sold at the farmer's market. Another thought. Then it comes up with the thought 9 of the eggs are sold at the farmer's market. A bit of a repetition. $2. That's the price of each egg. Therefore, 2 times this is 18. 18 is the total number of eggs. The total price of the eggs is 18. And that's the right answer. Do you see that, guys? And does it far more closely align to how humans would have reasoned? There is a little bit of redundancy here. That is true. We would probably not have thought a few so repetitively, but it is the correct response. Then the second time around, it didn't quite get there. She says so it sort of gets the reasoning right, but it never finishes it. Right? It gets into a loop where it is just repeating itself. So this one was not quite a success, but it made partial progress. The third one, once again, it gets the answer right. You see that? Third time it gets the answer right. A fourth time, once again, it gets the answer right. And fifth time, it gets the answer right. So it gets the answer right 4 out of 5 times. Do you see that? And it gets it partially on the right track the fifth time. One of the attempts, it gets it only partially on the journey to the right answer, but it gets into a loop, repetitive loop, right? Which hopefully they will remedy, future work will remedy. So I hope the results speak for themselves, right? The fact that it does make an improvement over the current state of the art, at least using Mistral, using a small model, the value of Quiet-STAR seems to be evident. And so with that, now I'll take questions. Was this paper relatively clear, guys?
The one thing that I couldn't quickly grasp is the thoughts that are generated. Is it internally generated?
Oh yeah, it's all internal. It is internal,
Correct.
but you can ask it to produce its line of reasoning. It will keep producing the output. But the important thing is, no matter what, whether you ask it to do a chain of thought or not, it will nonetheless internally keep thinking. Because if you go back to the architecture, look at this. And this picture is the crux of this. Let me go back up. You notice that, look at this main picture here in this. Do you see that it is thinking its thoughts no matter what?
Correct.
So it does keep internally thinking. That's why the word quiet. It is quietly thinking. And so what you have done is, and the crux of it, I suppose, is this very insightful statement they make. We instead ask if reasoning is implicit in all text, why shouldn't we leverage the task of language modeling to teach reasoning?
Mhm.
That is the key insight for us, on
As
which
if,
this argument. Yes.
as if in the example that was given, the 42 plus 12,
Yeah.
shouldn't it have gone from the digits place, so done 2 plus 2 first? Because
No,
there could
because
be a
it has to generate.
carryover. There could be a carryover that comes from the digits place into the tens place.
That is right. See, this diagram, don't overread into it. This diagram is there just as an illustration of the idea of the architecture. Right? So it is saying that if it has already produced 5, and it is about to produce what comes after 5, right? So the idea being that for 5, it must have used the second thought, and for the 4, it should use the first thought, the thought in the middle that is given there.
Got it. Right. So are you forcing this machine to generate a thought as to how it is
Yes.
used, or are you? Okay, got it.
Yeah.
Okay.
All the time. In fact, that is what this reinforcement learning machine is doing. It says, because thoughts can be wrong and it can be right, and the reinforcement learning is teaching it to basically generate more useful thoughts. And that is the value, guys. So let us summarize this paper. I will do that. What have we talked about? That a very practical definition of reasoning is that if you see it go through steps and produce the right answer, you say that it's reasoning through those chain of thoughts. So how do you make it? Key insight is, why don't we train a large language model to produce, basically be a language model to be a language model, which is have a language representation, a hidden representation, which captures the language in such a way that it produces the next token, in such a way that it does translations, blah, 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 etc. Right? But why should the representation internally, the whole process of training the model, also not implicitly have reasoning built in? Because you can't understand any text or represent a text unless you have some degree of comprehension of the text. In fact, that's why people use the word natural language understanding when you talk of language models. And they use this thing. And the main point is that they're not doing it for specific examples. Like, for example, the previous paper, STAR, was doing it specifically for question answers by giving a few short examples. Then, yes, it does better. But they're saying that, no, you don't need to do that. It is actually a more general thing. Reasoning is built into understanding text. If you don't infill some reasoning, some understanding, you can't understand text at all. Right? We all do it all the time. And so let's train the machine also to do that. And that is the main thought that they're coming up with. And then the results just speak for themselves. The rest is machinery. How do they do it? And there is the think, there is the talk, there is the the reinforcement learning parts, and so forth. And basic problem statement is that now you want to parameterize your large language model in such a way that the weights and biases in such a way that the log probability, or you maximize the likelihood of the tokens that you want to see, right? And that is conditioned on not just the tokens that you have seen so far, but also rationales, these thoughts that are generated. And they use the word, do you notice that they use the word non-myopic? It is built into that. You notice that they're saying from token I to token N that we're producing, maximize the probability. Tune your network so that the next few tokens depend on the prior tokens and the rationals. Prior rationals. Right? So that is it. That is the gist of this paper. I will, any comments on the record before I stop recording? And Murray, I noticed that you're having a bit of a problem. Stay back on Zoom after this and let's see if we can fix it. Any questions, guys? All right.
So I have a question, as if maybe you can record it or not. That's also fine with me. The reinforcement feedback, right? Somewhere where the equation where you showed, doesn't it also depend on the quality of the guys who are giving the feedback and how what kind
Oh,
of an
no,
expert they are in their
this
field.
part of reinforcement, actually comes pretty easily. You think a thought, you incorporate it, and the output is wrong. No, the
Right.
reinforced mechanism just penalizes it. It says, oops, you were misleading. It doesn't actually look at the answer. You don't have a human look at the answer. There's no human in the loop.
Or there is no human in the loop. So we cannot uh, train it to kind of twist its thinking in the right direction, right? That is not possible.
These machines have already been trained with human in the loop, right? So you started with Mistral 7B. It has already gone through pre-training, supervised fine-tuning, and human feedback alignment. You're further tuning. What Quiet-STaR is a process of further tuning the language model, right? And in this further training part of it, consider it a fine-tuning beyond that. In this fine-tuning phase, you don't bring a human into the loop.
So there is no expert comments over here to alter its path. It's basically it has to now figure out from that whatever the open web fine tuning.
No, simply, yeah. Whether it produced an answer. Oops, was it right or wrong? Oops, that wasn't right. Here's a penalty.
Okay, got it. Okay, thanks.
So that is your standard NL. That's why if you look at the equation, right, it's so well placed. It is, you notice that gradient of the loss of the negative log likelihood and the gradient of the loss of the parameters with respect to the reinforcement, reward punishment.
Right.
That's
yeah.
so
That's why I had the doubt. So okay, good. Thanks.